unit. So last week we discussed resolution of a vector in space along three orthonormal system of unit vectors, that is I cap, j cap, and k cap. And we also discussed the direction cosines. If this is a vector in space, the angle that the vector makes with the positive x-axis, the positive y-axis, and the positive z-axis is alpha, beta, gamma. Okay, that you know cosines of that is called as the direction cosines, represented by L, M, and N, and squares of the direction cosines is equal to sum of the squares of the direction cosines is equal to 1, and each of the direction cosine is defined like this: x upon root of x square plus y square plus z square, which is x upon r, which is L. Cos beta is y upon r, which is m, and cos gamma is z upon r, which is n. And r bar is r cap, that is the unit vector along this OP, will be L I cap plus M J cap plus N K cap. That means the coefficients of the unit vector gives us the direction cosines along I, J, and K. So direction cosines L, M, and N. So with respect to I, J, K. So this is the addition of vectors. So very simple calculations. Let us do one simple examples. You please calculate and tell me. Find the direction cosines of the vector, say 2 I cap minus j cap plus 3k cap. So please find L, M, and N. What are direction cosines? Cos alpha, cos beta, cos gamma. X upon under root of x square plus y square plus z square, y upon under root of x square plus y square plus z square, and z upon under root of x square plus y square plus z square. So please calculate this. Give your answers. Yes? No answers?
Sir, 2 by root 14 minus 1 by root 14 and 3 by root 14.
Very good. So R is under root of x square plus y square plus z square, which is under root of 2 square plus 1 square plus 3 square, which is under root 14. So cos alpha or L is 2 upon root 14, that is x upon r. Cos beta, which is m, is minus 1 upon root 14, that is y upon r. And cos gamma is 3 upon root 14, z upon r. It's cos alpha, cos beta, cos gamma. Okay. All right. Um, all right. One more. Find the direction cosines of a vector joining 2 points A 1, 1, 1 and B 3, minus 5, 4. 3, minus 5, 4. Yeah, please find. Please find.
Sir, 2 by 7 minus 6 by 7 and 3 by 7.
Yeah, okay. Let us do this. So first AB vector AB bar will be, this is the position vector of B minus position vector of A. So this is 3 minus 1 I cap plus minus 5 minus 1 J cap plus 4 minus 1 K cap. So we get 2I minus 6J plus 3K. So this is AB, modulus of AB bar, which is R, is under root of 2 square plus minus 6 the whole square plus 3 square. So this is 4 plus 36, 40 plus 9, 49. Under root 49 is 7. Therefore, the direction cosines cos alpha, which is L, which is x upon R, is 2 upon 7 cos beta is minus 6 upon 7 and cos gamma is 3 upon 7. Okay, so these are the direction cosines. So this each of these values represents cos of the angle made by the vector with respect to the x-axis, y-axis, and the z-axis. So that is about the direction cosine. It's a very, very important concept. So fundamental to understanding of vector algebra. So once we have covered direction cosines, now we have this important, next very important one is the multiplication of vectors. First one beginning with the scalar product. So multiplication of vectors. So two vectors A and B, the scalar product of two vectors AB is given by A dot B, and this is defined as modulus of A, modulus of B, cos theta. Okay, where cos theta is the angle between the two vectors A and B. Now, how do you calculate the angle between the two vectors A and B? So let's say this is vector A and this is say vector B. This is vector A and this is vector B. What we do, we make them as co-initial vectors. That means take a line which is parallel and so we have to make both the vectors co-initial vectors because vectors are free. We can move the vector from one point to another, and the angle thus made once they are co-initial vectors. It should not be that one is an initial point, another is a terminal point. Then the angle made by both of them is the angle between the two vectors A and B. Now, cos of this angle is given by A dot B by modulus A modulus B. So A dot B is defined like this: A B cos theta. A B cos theta. Now it has some connotation. Of course, like theta has to vary between 0 to pi only, because after that, if you make co-initial vectors, the maximum angle between the two vectors will be pi. Greater than pi, again, it will have a counter angle. Suppose, let's say, this is vector A, one vector. Now, let's say there's another vector, you keep rotating. Let's say this is this angle. Now, when you take this angle is greater than 180. However, this angle will be less than 180. An angle between two vectors is defined as once you draw the co-initial vectors, the lesser of the two angles. You never take the greater of the 360. This angle will be theta minus 360. We don't take this. We take the smaller of the two angles. So that is why the angle will always lie between 0 and pi. Next, the properties of the dot product. These are all reviews, but very important reviews. And interestingly, in GATE, many questions come from the basic vector algebra, not as predominant as from vector calculus, but this basic understanding comes. So A dot B is equal to B dot A. It follows commutative law. And then vector dot product is distributive over addition. So distributive law works. A dot of B plus C is A dot B plus A dot C. And then A dot A is equal to mod A whole square. This is A dot A. Now two vectors A bar and B bar make an acute angle if A dot B is positive, an obtuse angle if A dot B is negative. This is very clear because cos theta from A dot B, here the cos theta is A dot B upon modulus A by modulus B. Okay, A dot B by modulus A into modulus B. So what we get is, now if angle is acute angle, cos theta, theta varies from 0 to pi, that much we know. Now if theta lies between 0 and pi by 2, cos theta will be positive. So if theta is acute, then cos theta is positive, which means, look at the right side, the denominators are modulus, so they will always be positive. So which means the dot product will be positive. If theta is obtuse, then cos theta will be negative, which implies A dot B is negative. All right. Now, if theta is perpendicular, sorry, if theta is 90, not that means the two vectors are perpendicular, then cos theta is 0, which implies A dot B is equal to 0. So this is a very important property. A dot B is equal to 0 if the two vectors are perpendicular to each other. For two perpendicular vectors, the dot product is, their dot product will be 0. Now next, look at this fifth property. A dot A plus B the whole square. This is taken as A plus B dot A plus B. Now we do the usual operation. Multiplication is distributive over addition. So we use that concept. So you get A plus B dot A plus A plus B dot B. Then again, multiplication is distributive over addition. So you get A dot A plus B dot A plus A dot B plus B dot B. Now A dot A is modulus of A into modulus of A into cos of the angle between the two identical vectors. Cos of the angle is 0, cos 0. So you get A square. That means modulus of A, if we just write as modulus of A bar, if we write as A square, A, then this will be A square. Now A dot B is same as B dot A, commutative law, and this B will write as B square, and this becomes 2 times of A dot B. So that's what this is. It is A square plus B square plus 2A dot B. Now similarly, A plus B dot A minus B, A plus B dot A minus B. We'll get A dot A, I'll write directly, minus A dot B plus B dot A plus, sorry, minus B dot B. So this is A square. Now this A dot B is same as B dot A. So we can write like this. So this and this cancels. So we get it is A square minus B square. Rule of dot products. So when we use the orthogonal 3D three-dimensional space, the orthonormal unit vectors I, J, K, then the dot products work like that. So I dot I is 1. This is, yeah, sixth property. So I dot I will be 1 into cos 0. J dot J is 1 into cos 0. K dot K is 1 into cos 0 again. So I dot I, J dot J, K dot K is 1. So I dot J is equal to J dot K is equal to K dot I is equal to 0. Why? Because they are perpendicular to each other. I and J, I is along the x-axis, J is along the y-axis. The angle between them is 90. Cos of 90 is 0. So modulus of I into modulus of J into cos of 90. So we get 1 into 1 into cos 0. So cos 90, which is 0. So this, when we extend to two vectors, let's say I'll just maintain the notation A and B. If A is A1 I cap plus A2 J cap plus A3 K cap, and B B1 I cap plus B2 J cap plus B3 K cap, then when we do A dot B, so it is A1I plus A2J plus A3K dot B1I plus B2J plus B3K. So when we take dot product, what do we get results? I dots with I to give 1. So with the coefficients, we get A1, B1. Then I dots with J to give 0. I dots with K to give 0. Then J dots with I to give 0. J dots with J to give 1. So A2, B2 plus J dots with K to give 0. So K dots I to give 0, K dots J to give 0, K dots K to give 1. So we get dot product is just the product of the coefficients of I, J, K. So A dot B is this. Just a second. Yeah, sorry. Okay, A dot A1, B1, A2, B2, A3, B3. So Now cos of the angle. And what is modulus of A? Is under root of A dot A. A dot A is A square. So under root of A dot A, this is A1 square plus A2 square plus A3 square. And modulus of vector B is under root of B dot B. We get B1 square plus B2 square plus B3 square. Therefore, cos theta is A dot B by modulus of A modulus of B. So it is A1 B1 plus A2 B2 plus A3 B3 by under root of A1 square plus A2 square plus A3 square and under times under root of B1 square plus B2 square plus B3 square. So now this we know. This we know how to do this. This is a important review. Now let us move to the geometric understanding of a dot product, or geometrically the conception of projections comes from the dot product. So that's what let us go through. It's just a statement here, but it's means very important because we keep doing this all along. So projection of vector A along B bar is A dot B cap times B cap. How is this so? So let us say this is vector A bar and this is vector B bar. Now projection of A along B. Projection of A along B. So it is same as you take a line parallel to B bar. Line parallel to B bar. And then you take a component of A along the B direction. So this is the projection. The same projection, of course, you can extend the same projection along B bar like this. So the same vector you can shift this way. This will be projection of A bar along B bar. Now angle between A and B is theta. So if you make B as co-initial vector, you get theta. So now this, let's say this is A, B, and this is A, B dash. So A, B dash is the projection. A, B dash bar is the projection of AB along B bar. So isn't it? Projection means the concept of projection is this. See, let us say this is a wall and let us say this is an object, a straight line object. The projection of this object on this wall means what? It means that I take a light source from a very far distance such that the light source is parallel. Now this parallel rays of light source are perpendicular to this wall. Then the length of the shadow is the projection, length of the shadow of this rod. Let's say this object is a rod onto this wall. Is the projection of this projection of this object, the rod, on the wall. That means we have, parallel light source. So light rays moving parallelly fall on this rod, and throughout here, this portion is the shadow. So this is the shadow. Okay. So length of the shadow is the projection of this rod on this one. So like that, the projection of A bar along B bar, what did we do? We dropped perpendiculars from initial point and terminal point of the first vector onto the second vector, and then took its length. That is the projection. So now we know what is cos theta. Now, what is this AB by, from simple trigonometry, AB dash upon AB is equal to cos theta. The adjacent side by hypotenuse is cos theta. Now, AB dash is the required vector, which is AB cos theta. What is AB? Modulus of A bar times cos theta. Now we know that cos theta is the angle between the two vectors. So I multiply and divide by B bar, modulus of B bar. So what is my numerator? A bar, mod B bar, cos theta. This is nothing but A dot B upon modulus of B bar. So what I got is this length AB dash, the length, just the length is A dot B upon mod B. So AB bar length is, now I can divide like this. So I get A dot B cap. So AB bar is A dot B cap. So length of the projection of one vector along the other. So length of the projection of A bar along B bar is A dot B cap. Very important result. Vector algebra. So now if I want to find this vector A B dash bar, A B dash bar, that is AB bar times the unit vector along AB bar, its own unit vector. Now unit vector because the direction of AB dash is same as the direction of B bar. So this length AB times the unit vector. So length AB is A bar dot B cap times B cap. That is the projection. So projection of one vector along another vector is first vector dot the unit vector of the second vector multiplied by the unit vector. So this is the projection. And areas of parallelogram and all, we will see. This can be found using dot product. Next, look at the vector products. The vector product of two vectors we know is A cross B is defined as a vector C, which is mod A mod B sine theta n cap. Now cross product is defined like this. We all know if this is A, this is B in a plane, then let's say this is the plane containing A bar and B bar, then we will have the vector C bar outside the plane, perpendicular to the plane, such that it follows the right hand thumb rule. What is the right hand thumb rule? If we curl our right hand fingers from the first vector to the second vector, so right hand, the index finger, middle finger, ring finger, and the little finger, if we curl these four fingers along from A to B, if we are curling this, the direction of the right hand thumb will give you the direction of the cross product. So cross product, it is the cross product is a vector which is perpendicular to both A and B. That means it's perpendicular to the plane containing A and B. And the magnitude is AB sine theta. Mod A mod B sine theta is the magnitude, and the direction n cap is n is a unit vector along a line perpendicular to both A and B, and the direction of n follows the right hand system. So n cap is here. N cap is here in this direction. So C, the magnitude of C is this, and multiplied by a unit vector. So that is the cross product. That is how it's defined. The properties of cross product. The properties of cross product. A cross B is equal to minus of B cross A. They are not commutative. Cross product is not commutative. We know this. The reason A cross B, when we do, we are curling, the direction will be following the right hand thumb when fingers are curled from A to B. But when B cross A we do, from B to A, we curl the right hand thumb, right hand fingers. So the direction of the thumb, the right hand thumb will be downwards. It will be opposite of this. So for this. So naturally, this is a vector. Scalar product is a scalar. Dot product gives you a scalar quantity. Cross product gives us a vector quantity. That is how we define it. This is our definition. So by definition, A cross B will be equal to minus of B cross A. And again, by definition, A cross A will be 0 because sine of the angle between the two identical vectors is 0. Sine angle between the two identical vectors is 0. So sine of 0 is 0. Of course, the cross product is distributive over addition. So A cross of B plus C is A cross B plus A cross C. Now we have this important, very important relation with the orthonormal triads. The orthonormal triads. So I, J, K. Now I cross J will give us K. J cross K will give us I. So I, J, K write in a clockwise sense and draw clockwise arrows. Then we get the relation I cross J is equal to K. Then J cross K is equal to I. And K cross I is equal to J. I cross J is equal to K. J cross K is equal to I. K cross I is equal to J. All right. And if we go in a reverse cycle, reverse order, you will get negative. That is what J cross I, if we do, because I cross J is same as J cross I, I cross J is not commutative with J cross I. It is opposite. So J cross I will be minus K because our X, Y, Z coordinates follow the right hand thumb rule. From X to Y, if you curl the right hand fingers, then the direction of the right hand thumb will give us the direction of Z. Correct? So similarly, Y cross Z will give the direction of X. So that's all. So J cross K, K cross J will be minus I. And I cross K is equal to minus J. So we get these. And we also get I cross I is 0, J cross J is 0, and K cross K is 0. Now using this, so two non-zero vectors A and B are collinear if and only if. So if vectors are collinear, naturally their cross product will be 0. Now using these and these, using this and these, now when we do cross product of A and B, which are defined like this: A1I plus A2J plus A3K, and B is B1I plus B2J plus B3K, then the cross product is nothing but the determinant of the coefficients. Write I, J, K in the first row, then A1, A2, A3, B1, B2, B3. All right. Now I times, so just do the evaluate the determinant. So I times A2 B3 minus A3 B2 minus of J times A1 B3 minus A3 B1. So when you take the minus sign inside, you will get A3 B1 minus A1 B3 times J plus K times A1 B2 minus A2 B1. So this is how we find the cross product. How do we arrive at this? By actually doing a cross product route, just like the way we did the dot product here. Multiplying, if you take a cross, you will have 9 terms, 3 into 3, 9. So of the 9 terms, 3 terms will get eradicated and we'll be left with 6 terms, and that we can show that that is the determinant. Okay, so modulus of A cross B. Modulus of A cross B is mod A mod B sine theta times mod n. Mod n will become 1. Mod n cap will become 1. So what does this represent? This represents the area of a parallelogram. So area of a parallelogram whose two adjacent sides area of a parallelogram whose two adjacent sides are A cap and B cap. Sorry, A bar and B bar. Then we know the area of this triangle is, so what is area of this triangle? Half base into height. Base is A, height is B sine theta. So half AB sine theta will give us area of this triangle, multiplied by 2 will give us the area of the parallelogram. So AB sine theta is the area of the parallelogram, and half AB sine theta is the area of the triangle. So we get area of a parallelogram whose adjacent sides. This will be B sine theta. B is the hypotenuse. Opposite side in terms of the angle here is B sine theta. So area of the parallelogram whose sides are A and B, whose sides are along the vectors A and B, or vectors are along the sides A and B, is A cross B. And area of the triangle is half A cross B modulus. So A cross B is said to be a vector area of the parallelogram. So A cross B without the modulus, we say it is the vector area of the parallelogram. Why? Because the vector, the direction of the vector, area vector, the direction of the area vector will be perpendicular to the plane of the triangle or the plane of the parallelogram. This will be the direction of the area vector. So generally we don't show it at the end. The area vector, we show the direction of the area vector perpendicular to the area. So area, so far we studied that area is a scalar, which is true, but there is a conception of area being the vector, that the actual geometric area represents the scalar magnitude and perpendicular direction represents the vector. So there's the concept of area vector. So, and this area vector, we know this is A bar, B bar. So A cross B, curling the fingers, right hand fingers from A to B, and we get the direction of A cross B as n cap. So that is the direction of the area. Okay. So area can be a vector quantity. A unit vector perpendicular to the plane of A bar and B bar is A cross B by modulus of A cross B. So a vector perpendicular to the plane of A bar and B bar is A cross B. A vector which is both uh, perpendicular to A as well as B. That means it is perpendicular to the plane containing AB. That is AB bar. Now unit vector divide by the modulus of A cross B. We get this. And the vector of magnitude lambda in the plane perpendicular to A bar and B bar is multiply this unit vector by lambda. So next, the concept of triple product and product of scalar product of scalar and vector product of four vectors. So very quickly we'll cover. We'll not have too many questions on this from gate point of view. But it is an important result which can be very handy, very useful to us. So scalar triple product of three vectors A bar, B bar, and C bar is defined as cross product of two and dotted with the next one. So A cross B dot C. And it is also same as A dot B cross C. So cross product of two with a dot with the other. Now this will remain same as long as the cycle ABC is maintained. So this cycle ABC cycle, then if we start with BCA, after BC comes again A. Or if we start with C, after C comes A, CAB. So as long as this cycle is maintained, then the scalar triple product, also called as the box product, will be the same in sign also. So you see ABC, ABC, BCA, CAB. As long as this is maintained, the cyclic order is maintained, ABC, then the scalar triple product will have the same sign. It is a scalar. It will have the same sign. It will have the opposite sign if ABC, BCA, CAB, they will have the same sign. But BC, no, this should be BAC minus B starts with B, A, C. Now the cycle A and B have been exchanged from ABC. A and B cycle has been interchanged once. So this will be negative. So BCA and minus BAC. Similarly, CAB and CBA, this will be having opposite signs. Why? Because cross products are not commutative. C cross A will be equal to minus of A cross C. So that is why this negative sign comes. Now, the scalar triple product of three vectors defined by A1I plus A2J plus A3K, B1I plus B2J plus B3K plus C1I plus C2J plus C3K is equal to modulus of the three A1, A2, A3, B1, B2, B3, C1, C2, C3, modulus of the coefficients. I'm sorry, the determinant of the coefficients. This represents the volume of the parallelepiped whose adjacent sides are vectors a bar, b bar, and c bar. What is a parallelepiped? It is a three-dimensional prism kind of a structure in which it is a rectangular kind of a structure, but whose adjacent sides are inclined. So there's not necessary that any two sides are perpendicular. All sides can be inclined, but the faces are parallel, which means the opposite faces are parallel, which means the sides, the four sides containing the opposite faces or the four edges are parallel. Any four edges you take are parallel. Four edges containing the opposite sides, opposite faces, they are parallel. So it's a parallelepiped, area of the parallelepiped. Sorry, volume of the parallelepiped. Now, altitude of a parallelepiped we can find. Okay, if h is the altitude of the parallelepiped, theta is the angle between the vectors BC and alpha. Okay, this is not required for you. We'll just skip this. The volume of a tetrahedron ABCD. What is a tetrahedron? This is sometimes very useful even in general aptitude type of questions. Now, tetrahedron is an object whose all sides are triangles, and if A, B, C, D are the edges of the triangle, A, B, C, D are the edges of the triangle, then what we get is, you take these vectors AB bar, AC bar, AD bar, AB bar, AC bar, AD bar, and then take its box product or the scalar triple product of AB bar, AC bar, and AD bar, and 1/6 of this gives the volume of the tetrahedron. Okay. All right. So three vectors will be coplanar if the scalar triple product is 0. This is an important result. Rest is not. And then there is, based on distributive law of addition, or multiplication is distributive or addition, we get this. Not so critical for us. And scalar product of four vectors, cross product of A cross B dot C cross D is modulus determinant of A dot C, then B dot C, then A dot D, and B dot D, a determinant of this. Okay, scalar triple product defined very, scalar product of four vectors defined simply. Last part, we'll not go into geometric applications of vector equation of a plane now. We'll consider that later. Now, vector triple product. Now, A cross or B cross C. Now, B cross C is a vector perpendicular to both B and C. Now, A cross B cross C will be a vector which is perpendicular to A and is also perpendicular to the perpendicular of B cross C. That means the direction of B cross C. So this A cross B cross C will be a vector which will lie in the plane of BC, but it will be perpendicular to A. So that is what we see. You get a linear combination of vectors B and C. That means this A cross B cross C lies in the plane containing B and C. Very simple. Just an illustration. This is B. This is C. Now, let's say this is vector A. Now, a vector which is perpendicular to both. So this is B cross C, let's say direction of B cross C, which is perpendicular to the plane of B and C. Now, A cross B cross C, A cross B cross C is a cross product of these two vectors, A and B cross C. Now, the cross product of two vectors will be perpendicular to both the vectors. So, any vector which is perpendicular to B cross C will lie in the plane of B cross C. So, this lies in the plane of B cross C, but it will be such that it will be perpendicular to A. A cross B cross C. This lies in the plane of B and C, but it will be perpendicular to A. That is the triple product. Similarly, A cross B cross C will lie within the plane containing A and B, but it will be perpendicular to C. So how do we calculate? Extremes, dot product of the extreme first, A dot C times B bar, then minus the dot product of the near ones, A dot B times C. Similarly here, A dot C times B minus B dot C times A. So this is how we calculate the vector triple product. Okay. This third point is what I explained just now. And vector product of four vectors, not so important for us. So with this, I cover the vector algebra part. Okay, let's do some problems on vector algebra, which comes in gate here. Already answers are there, but let us do that. Questions on vector algebra here. So area of the triangle formed by the tips of vectors A bar, B bar, C bar. Although the answer is given here, I want an explanation how this is done. Anyone would like to volunteer? Area of the triangle formed by the tips of vectors A bar, B bar, and C bar. What do you mean by tips of these vectors? Anyone? No one is answering. You can put in the chat. What do you mean by the tips of the vectors? What are these vectors? A bar, B bar, C bar.
It's three sides.
Sides of what?
Means vector, three vectors that will form a triangle.
Okay. Just a second. This. Okay, let's take this. This is a space. A bar, B bar, C bar are position vectors of 3 points. Okay. A in space, B and C, let us say. So this is A, B, C. Now, if I draw a vector, they're not necessarily coplanar. They 3 points will always be coplanar. That is true. So they're not necessarily, Now, these vectors I draw from the origin A, B, B bar, and C bar. This is A bar, B bar, C bar. Now, area of the triangle formed by the tips of these vectors means by the endpoints of these vectors. So the triangle that is formed is this triangle in space. All right, this is the triangle ABC. Clear? So the position vector of A is A bar, position vector of B is B bar, position vector of C is C bar. That is the idea. Now, adjacent sides of the triangle, any two sides of the triangle. Let us take AB bar and AC bar. Okay. Now, when you take the cross product of AB bar and AC bar, that will give you the area of the parallelogram whose adjacent sides are this. Now, area of the triangle will be ABC will be half of modulus of AB cross AC. Correct? Half modulus of the two adjacent sides of a triangle. Got it? Now, AB bar is position vector of B, that is B bar, minus position vector of A, cross position vector of C minus position vector of A. Now this, now you take minus sides from both the factors. So multiply both the factors with the minus sign, you get this. Area of triangle ABC is this. Half determinant of half modulus of A minus B cross A minus C. So this is the answer. It's not dot, it is a cross product. So this answer is wrong, this is wrong, this is wrong. Clear? It was a simple question, not a difficult question. But just that, we just have to have the right concept of it. Let's do another one. This will be easier. I'll remove the answers for now. So that this angle between two planar vectors. Okay, angle you can do. So let us do this one. Third one. If A and B are two arbitrary vectors with magnitudes A and B, then modulus of A cross B the whole square. How do you do this? From the given options. Anyone? No one? Any one of you? If you got answer, you can raise your hand. Simple. Look at this. A cross B, a whole square, modulus. A cross B is modulus of A, modulus of B, sine theta times n cap whole square. So A, B, sine theta are scalars. So you get A square, B square, sine square theta, mod n cap whole square. Mod n cap is 1. So we get a square b square sine square theta. The sine square theta we can write as 1 minus cos square theta. This is a square b square minus a square b square cos square theta. Now what is ab cos theta? Is a dot b, the whole square. A square b square minus a dot b the whole square. So this is the answer. All right, very simple, just a simple arithmetic simple trigonometric manipulation. That's it. So next one. Hmm. If A, B, and C are 3 points, then which one of the vectors is perpendicular to the both A bar, AB bar, and BC bar? So what do you have to find? Cross product of, just find this cross product. I'll You solve it. And those who finish this, you try one more. So please attempt these two questions. I'll just join in 2 minutes, 2, 3 minutes. You solve these two questions till then. Okay, back. So the first one here, AB bar is B bar, coordinates of B bar minus A bar. So 0 minus 0. So 0 I, 0 minus 4. So minus 4J, 0 minus 3 minus 3K. This is AB. BC bar is C bar minus B bar. So C 3 minus 0, 3, 0 minus 0, 0, 4 minus 0, 4. So this is minus 4J minus 3K and 3I plus 4K. So which one of this is perpendicular to both these vectors? So we have to look at the cross product. So cross products, of course, we can do using the determinant form. So 0 minus 4 minus 3 and 3 0 4. So you get I cap times minus 16 minus 0 minus j cap times 0 minus j cap times 0 minus of minus 9 is plus 9 plus k cap times 0 minus of minus 12 plus 12. So we get okay, minus 16i minus 9j minus 16i minus 9j plus 12k. So minus 16i minus 9j plus 12k. Now A cross B cross C, sorry, AB cross BC, we have got this. Similarly, the minus of this will be BC cross AB. Will be negative of this, that is 16i plus 9j minus 12k. So both of these vectors will be perpendicular to both A bar, AB bar and BC bar. So now compare. So we have 16i plus 16i plus 9j minus 12k. So this one is perpendicular. Here the combination is different. 16 in these two, 16 and 9 have opposite signs, but we should have the same signs. So these two are not. And here 16 and 9 are of same sign, but 12 is also of the same sign. But we have 16, 9 and 12 are of opposite signs. So that's why A is the correct one. Now for a parallelogram OPQR, OP is parallel to RQ. So let us draw the parallelogram. OPQR. So OP is parallel to RQ. OR is parallel to PQ. Okay. As shown in the sketch. Okay, I'm giving the sketch now. Now OP bar is AI cap plus BJ cap. OR bar is CI cap plus DJ cap. Now what is the area of the parallelogram? Area of the parallelogram will be modulus of OP cross OR. Adjacent sides, right? So let us do the cross product. Okay, we'll get K in terms of K, because this is an IJK. All right, IJK A B 0 C D 0. So I times 0, J times 0, and K times AD minus BC. K gap modulus. We get AD minus BC. So AD minus BC is the answer. All right. So these were some questions on vector algebra. So you can see from vector algebra, we get questions, and this is only a sample from of GATE from I think 2004 to 2014. The rest I have a bank, but that I will give you for uh, practice tests. So that not within class practice, I'll give otherwise. So you can see that we get questions from vector algebra. Not that it is, of course, vector calculus is so much more we get, but most of the questions are from vector calculus. But vector algebra cannot be neglected. So next is this topic of vector differentiation. The differential calculus of vectors. So first one, okay, differentiation of vectors. So let R bar, which is a function of a variable t, or it is a function of t. R bar is a function of t, be a vector function. That means as t changes, the value of the vector and even the direction can change. So let f be a vector function, or r of t, which is f of t, be a vector function varying continuously with a scalar variable t. Then we define its derivative as dr upon dt is equal to limit delta t tends to 0, r of t plus delta t minus r of t by delta t. Okay, or this also can be written in terms of f limit delta t tends to 0, f of t plus delta t minus f of t over delta t, vector functions. So the derivative is also a vector. So you get a vector. Now let us see the geometrical interpretation. So application to plane curves. Curves in space. So let r of t be, say, x of t I cap plus y of t j cap plus z of t k cap. Now b the position vector. Let r be the position vector of a point as a function of the scalar parameter t. Okay, so for different values of t, the point P traces a curve in space. So let us do that. Let us draw the spatial x, y, z. This is origin. Now this the curve, let's say, is like this in space. It's a spatial curve. Now at a given instant t, this is the position vector of a point. Now at an instant t plus delta t, generally it's like a time, t is time, but generally a spatial points. So t plus delta t, let's say the parameter t, let's say time, changes by delta, and the point just moves there. Now delta t, actually it should be very just close to delta t is so small that it is very close, but to draw the figure correctly, we are taking it little away. So r of t and r of t plus delta t, there are 2 points. Now the difference between these two is what, like, uh, is this vector from the addition. When we take this, is this vector. Let's say I call this point as P, and after delta t, this point P moves to Q. All right. Now, what happens when delta t tends to 0? When delta t tends to 0, okay, I'll draw the same curve. Hmm. So now what happens? When delta t tends to 0, I just want to remove this red line. It's maybe difficult to remove. Ah, good. So now, if delta t tends to 0, this point Q will be just next. It will be just next to this P. So what we get when we draw this line PQ, we'll get a tangent, isn't it? This PQ bar here, position vector of Q minus position vector of P. So this is R bar of T plus delta minus R bar of T. So in this, the numerator is a vector which is in the direction of PQ, divided by the delta T. Now, if delta T becomes very, very small, so this length PQ becomes very, very small. Now, as delta T tends to 0, PQ bar becomes a tangent at P. So just like in our um, application of derivatives to functions of single variable in uh, the calculus that we discussed, the derivative represents tangent to a curve. So here, the derivation, a derivative of a vector is another vector which is tangential to the curve at that point where the derivative is being found. So therefore, very, very important what I'm writing. Therefore, dr by dt represents the tangent vector to the curve at P. So this is a tangent. Now, let us take some important case note. Now, if R of t has a constant magnitude, but its direction keeps changing, then if R bar has a constant magnitude, but its direction keeps changing, which kind you can find? which could be, it can be a radius vector of a circle. Now constantly it is changing. The radius vector r bar of t, the magnitude remains same, but the direction keeps on changing. So from one point to other point, the direction of vector changes. Now at any given point, say P, at any given point P, the derivative is the tangent. So this represents dr by dt. This represents dr by dt. So dr by dt, and interestingly, dr by dt is perpendicular. All right, it is perpendicular to r. All right. So here, if this is the case, if r has a constant magnitude, its direction keeps changing. So this is the radial vector kind of a thing. So in this case, this r dot dr by dt will be equal to 0, since dr by dt is perpendicular to r. Okay. In other thing, it need not be so. The tangent is, it is tangential to the path of the curve. But here the path of the curve is a circle. So the tangent will always be perpendicular to the radial line. Okay, this is number one. Number two, if r of t has a constant direction, but magnitude changes. All right. So dr by dt exists like, but it is like, this is r, and in the same line, I'm not showing purposely, but it is like, this is at time t, and this is at time t plus delta t. So difference will also be along the same. The difference will only be in terms of the length r of t plus delta t minus r of t. The difference will only be in terms of the length, not in terms of direction. So in that case, this r and so the derivative by delta t will be dr by dt. So r and dr by dt will be parallel. So r bar and dr by dt are parallel. So we have taken two extreme cases. One case in which the derivative of a vector is perpendicular to the original vector. Second case is the derivative of the vector is parallel to the original vector. In the first case, the magnitude is constant, the direction is changing. In the second case, the direction is constant, but the magnitude is changing. So in this case, r cross dr by dt will be 0. Because they are parallel vectors, the cross product will be 0. Now, there are some basic properties of derivatives, rules for vector differentiation. These are some fundamental concepts of vector derivative. Now, rules of vector differentiation. So, general rules. Hmm. So, if there are three vectors u, v, w, the sum of the derivatives, or the derivative of the sum is same as the sum of the individual derivatives. Okay. Therefore, note that derivative of xt of I plus y of t of j plus z of t of k is derivative of x times I plus derivative of y times j plus derivative of z times k. Why? Because actually you will have to apply uv each time, but I cap always remains I cap. So derivative of I cap is a constant in one sense. Its magnitude is constant and direction is constant. So derivative of I cap will be 0. Derivative of j cap will be 0. Derivative of k cap will be 0. So derivative of a vector in terms of ijk is equal to a vector of the derivatives of the individual components. Now, suppose there is a scalar. This is important. Now, scalar is a function of t and a vector is also a function of t. And let's say we are differentiating with respect to t. Okay. In other words, s of t times u of t derivative, it means that we are differentiating with respect to t. Then uv rule applies. Derivative of the first function keeping the second as it is plus keeping the first as it is derivative of the second. So just uv rule of differentiation. Now uv rule for this was a scalar multiplied by vector. Uv rule, this is vector dot product, derivative of vector dot product. So we get u dot v dash plus u dash dot v. Same uv rule, just that in between the product is maintained. Then same with the cross product. U cross v whole derivative is u cross derivative of v plus derivative of u cross v. Do not change the order of the vectors. Very important. That's all. The order should maintain same. Now, if it is UVW, the scalar triple product derivative of scalar triple product. So derivative of the first function keeping the other two same with the triple product. Then derivative of the second keeping the other two same plus the derivative of the third keeping the other two same. Same is applicable to the vector triple product. Keep the order of the vectors same. Do not change the order of the vectors. So first, in the first term, derivative of u, in the second term, derivative of v, in the third term, derivative of w. Okay, so this is the general rules for vector differentiation. Okay, I'll introduce a small concept. Tomorrow again, we'll get into detail. This is the most important concept in this whole vector calculus is, scalar point functions and scalar fields. Then we have vector point functions and vector field. Now, to just give an example, um, of a, you know, of a scalar point function, let us take a room. Room is a three-dimensional space in a room. Okay. Now, room has, windows, and then there is, sunlight falling on one side. All right, sunlight is falling on one side. And let us say, there is a AC, air conditioner, in one side of the room. Now, naturally, the temperature in the room, the heat is coming from the window, heat is coming from the sunlight through, diffusion through the walls. And there is the AC, which is spreading the cool air also. Now, that if we want to study AC, let's say it's fixed for 24 degrees centigrade. It is not the, or 20 degrees centigrade. It is not that the entire room will be at 20 degrees centigrade. Now, if you fix the origin, if we fix the origin at one end of the room, and there are infinite points in this space here. Now, temperature at any point in the room is a scalar point function, because temperature is a scalar. temperature at a point in a room. Now the temperature will not be identical throughout the entire room. There will be variations. And in fact, if you don't have an AC, and let's say there will be a significant difference in the temperatures. So temperature is a scalar point function. So temperature at a point x is a scalar point function. Now, at any given instant of time, you map the temperatures at all the points in the room. Okay, simultaneously, you are finding the value of temperature at all the points in the room. Then that becomes the temperature field. The temperature plot, or the value of the temperature, or the temperature function at every point in the room, plotted at an instant of time. So it gives a full map of all the temperature throughout. And now as the time keeps changing, the temperature keeps changing in the room. So we say that there's a field, scalar field function. So the function with respect to a particular point in space, a quantity is varying with respect to a particular point in space. With respect to space, it is varying. And let's say with respect to time also, it is varying. That means at every given instant, the t will keep, if x, y, z all are dependent on t, then it also changes. Now, there's an example of a temperature function, but it can be many other things. Tomorrow, when we begin, I will start with vector point function and vector fields. So this is a concept of scalar point function and scalar field. We will also study vector point function and vector field in tomorrow's class. So tomorrow's class, you don't miss it. Don't be late. I have to go out in the afternoon, but I'll try to be back by 4. It's important for me to cover tomorrow's class. It's a very important class because I'll introduce the concepts of divergence. I will introduce the concept of del operator, divergence, gradient, and maybe curl if I have time. So, and these are very important concepts, and how they are applied in various physical contexts, we'll have to learn that. So please join tomorrow. Thank you.